Hello lovely people, and welcome back to the channel. In this video I will go over all of the hardware that drives Nova, including the hardware setup and calibration, a full parts list review, wiring tips and suggestions, and the installation and assembly of the components and circuits. This is the third video of 4 in the NovaSM3 build series, so if you haven't watched the other videos yet, click the card above or in the link in the description below to the full video series playlist to catch up on the build. And as always, please like, share, and subscribe, and I hope you find this build series helpful or interesting at the very least. And if there are any particular pieces of the project that you'd like further videos specifically created for, please post your suggestions in the comments below. This is going to probably be a long video, so let's get started. Not all the parts listed are absolutely required to build Nova. Components such as the IMU or the PIR sensors, the MP3 player, and others all have their own software switches, which I coded for use during development and testing. However, they're also now served to allow us to disable pieces of hardware for whatever other reasons. We will go over all the software switches in the next build series video, which will be about Nova's software configuration, installation, testing, and usage. And also, some components do not have to be the exactly specified ones listed, such as the PIR sensors, or in the case of the MP3 player and speaker, for example, it was upgraded to a different version. It used to use this, I should say, lower grade version maybe, or older version. This is called the Pro version. This one uses an SD card, and the speaker that comes with it is not the greatest. So yes, there was an upgrade done there. And there were slight changes to the mounting part and the software libraries. So just keep in mind of any different parts that you may want to swap out, their fitment with their mating 3D parts in some cases, and of course any potential differences in wiring. Motor specifications are not also absolutely critical. However, keep in mind two things when it comes to the motors. Number one, the physical dimensions of the motor, and again, its fitment with its mating 3D parts. And number two, most importantly, remember, like with many other things in life, you get what you pay for. The 20K all-metal gear servos can be found for around $20 each, and they are the safest bet for this project. And in a previous video, which I'll also link in a card above in the description below, I upgraded 4 of Nova's servos to 35K ones, which are around $30 to $35 each. And although tempting at around $6 a piece, sorry for the sigh, but please refrain from using any of these MG996 servos for this particular project. A lot of people have asked, and I've seen a lot of people have tried, and it's a waste of time and aggravation, guys. And a final word on component selection and specifications. Along with this project's evolution over the past 14 months or so, have come many major hardware changes and upgrades along the way, such as I explained, the MP3 player, and then we also went from a modified PS2 remote to a fully custom DIY remote, and from multiple DIY circuit boards to a single simple custom PCB. So hence the need for this build series of videos to hopefully help new and current builders alike get the latest specs on how to build Nova without sifting through nearly 80 videos on my channel. They're all still great to watch and reference, as much of the content still applies, except perhaps where certain upgrades were made. Okay, so let's quickly run over the list of parts, and I'll talk about them as we go through them. Over on Nova's website, under Files and Parts, under NovaSM3, we have the full parts list. In here is also the latest links to the latest wiring diagrams, STL files, the code files, and then the MP3 sounds, all available on GitHub. And we've already done the 3D parts. This time we're doing the electronics. The PCB is available, has been for a while, but that also is sort of optional. You could still use the DIY boards if you want to, which I won't talk about here. There's the whole videos for all that. But I can show you if you want to order the PCB. The link takes you here to the project page. And then if you want to build your DIY boards, these photos and diagrams and such are all still available on GitHub. I think it's back to version 5. So let's dive right in, guys, and go through this list quick. It's a pretty long list, so I'll move pretty fast. First thing is the Teensy 4.0. So yes, people have asked me why Teensy, why 4.0. I think you're pretty much welcome to use whatever version you would like to. There shouldn't be any code that would affect that, I do not imagine. And then wiring and pin and all that stuff, I couldn't tell you. I'm not that familiar with Teensy, but enough to have made a huge improvement by replacing our Arduino Mega with this Teensy. Then number 2, we have basic Arduino Nano. I did manage to estimate cost here, but I think I explained in a previous video that this is based on the single item that you'd need for the project. So in this case, you can get 3 for 28 bucks, so I just put $10 for that. Okay, next is a 12 amp DC to DC step-down buck converter. Very, very important that it is 12 amps or larger. Okay, and then next we have the smaller buck converters, buck boost converters, it really is, but where we step down with it. And this is to get our 5 volts out for our microcontrollers. Then we have this little mini DC voltmeter for display that goes on the back of Nova so we can monitor battery voltage. And then these dip switches are for the PCB. So you do not need them if you are not using the PCB. And yes, it's something like this. When I mentioned costing, it's difficult. So I just threw $1 in there for these because you're only going to use 2 out of that whole kit. So very estimated cost. Then you need a couple of resistors for the voltage divider, which most of you probably already have on hand. And things like switches, yes, they're optional, but keep in mind holes are already made in most of the parts for things like this. So if you don't have the same size switch or part, either change your STL files or get the right sized parts. Okay, this is pretty important, very important to use a high current switch for this first switch, which connects your battery to that high amperage buck converter. It's going to be a lot of heat passing through those wires and switch, so make sure you don't use a generic one that can't handle it. Okay, then we have the batteries. Very optional, whatever brand, doesn't matter, but yes, must maintain and make sure that high discharge batteries, because they do have to push out quite a bit of amperage in short bursts. 16-channel PWM controller for the servos. Then we have our servos. Now, yes, here you can get flexible. You can save yourself some money. You can shop around, buy cheap ones, buy more expensive, better ones even. And then in the case of me, I upgraded 4 of my servos to these guys, which, yes, are not cheap, but it made a huge difference. And next we have servo extensions. Pretty important, I think. Not all of your servos will need them, but if you're happy cutting up wires and soldering on your own connectors, then you can omit this part as well and just make your own wires. Then you have your bearings, 8 by 16 by 5 millimeter bearings. That's why they're 8, 16, 5 millimeter. And then we have our aluminum servo horns. Now we have our PIR sensors, addressable LEDs. Then we have our ultrasonic sensors, very common device. We need 2 of those for Nova. Okay, then we have our IMU. This goes on the Nano circuit. We changed this along the way somewhere to an SPI version. The Nano is already on as a slave on the I2C bus to the Teensy. So then to have it act as a master and this as a slave within the same circuit just was not possible. So we had to switch over to an SPI display for Nova here. A little more expensive, but not much. But we get the benefit of full color, which is pretty cool. Here is the Pro version of the MP3 player, which I cannot find anywhere else but on DF Robot's site itself. But it has onboard storage, 128 megs, so it's pretty cool, and also uses USB-C, and it's a little bit smaller than the other version. These are the speakers that I got for mine, picked up on the side too. They're better than what comes with the DF players that you'll pick up on Amazon. These are 3 watt, 40 ohm, and they make a huge difference than the cheesy little ones that come with the DF player non-pro, which is right here. My suggestion is for the couple extra bucks, I would go with the pro version. And then lastly, we have a handful of ancillary parts like these switches. These terminals you will need whether you do the PCB or not. If you do the DIY PCBs, you will have to do a terminal block as well. And then if you don't do the DIY, you won't need these prototype PCBs. And then for the heck of it, I threw up the PLA as well. They don't even have the purple TPU that I used, so I had to link to blue. But anyhow, use whatever you want in those cases, but you should use TPU for the feet. This wire is awesome, guys. Let me tell you, I tried it a year or two ago, and I love this wire. Can't say enough about it. And then, yes, I still use hookup wire for cases where I don't want it to be flexible mostly, or for any PCB work. This little kit I picked up, I don't recommend it because, or at least maybe I'm not doing something right, but this crimp tool doesn't seem to work right with the JST connectors. It could be something I'm doing. I did create a whole video on that, and also just in general how to use the JST connectors, so I'll link to that in a card above right here. Hardware, as far as nuts and bolts and screws go, this one kit will probably cover it all. I know with the new shoulders, we use a couple of M2s, and actually they're a little bit longer than you'd find in most kits anyhow, so those you'll probably have to pick up separately. I'm 99% sure this kit will cover everything you need. Now on to the fun stuff, preparing to assemble and wire everything up. So there are schematics and diagrams available on Nova's website and GitHub, which linked in the description of all of my videos. Though please bear with me, I'm not an electronics engineer, so feel free to ask me any questions where clarity is needed regarding the schematics and wiring and diagrams. And you could also join Nova's Discord server, where the community is so very helpful to one another, and I've also done several videos on these topics, all of which I'll link to in the description below for reference. So first, let's talk briefly about hardware setup, configuration, and testing. There are a few components that need a little preparation before we can use or install them in Nova. The first would be the buck converters. As with all adjustable buck converters, we need to precisely set the output voltages for our 2 converters. The high amperage converter should be set to the nominal required motor voltage of 6.8 volts, and the smaller buck converter should be set to nominal MPU device voltage of 5.4 volts. Okay, and I won't bother describing how that's done. There are plenty of videos out there how to do it. It's basically putting your expected input voltage on it, dropping your voltmeter on there, and then adjusting the potentiometers to suit to get the voltage that you want, the output voltage that you want. Then I've also seen a lot of people will actually glue the dials on the potentiometers to ensure they never move, which isn't a bad idea, guys. In the case of these, they're really small and require a screwdriver, so it's unlikely they'll get moved on their own. Okay, and then the PWM controller. Since we're driving high amperage motors with this device, and 12 of them, we need to add a larger capacitor for stability on the power. Adafruit has a suggested formula on their website for this board, and so using that, I ended up using a 1000 microfarad capacitor for this project. This device is also an I2C device, and therefore may need its address set, which you could do with these pads right here on the top of it. You just solder across one of them to select your address, though the default normally is fine and has always worked for me, unless in the case where I've daisy-chained a couple of those boards together. Then you have to give them each a different address. And then the Teensy. In order to use external power with the Teensy, which we will be doing with our battery, and subsequently, or I should say simultaneously, use the USB interface with our computers for code uploading and powering the Teensy, there's a power pad underneath here that has to be cut, else you risk power surging your USB devices if both external power and the USB are connected at the same time. Yes, it can surge the power back through the USB, whatever's connected to the USB. So that's very important. Now, there's a video in my library demonstrating on how to cut that pad. Again, linked in the card below in the description. Okay, and then the NRF transceiver also has an I2C address, and in this case you're most likely going to have to play around with that. That's the most difficult part of getting this guy to communicate, because it uses a common set of addresses. And once again, there's another video from the library discussing this already, so I'll link to that above and below in the description. And lastly, it also requires a 22 microfarad capacitor to stabilize its power so it gets its solid 3 volts that it wants to get. Okay, so let's finally have a closer look at all of the components laid out here. Somewhat how they will go together, sans all the wiring, obviously. Standard best practices apply with all electrical work, such as connectors that you use, the pin headers, soldering technique, heat shrink tubing, and the like. And luckily I had most of the parts on hand except for 12 motors and the main power switch. A few tips about wiring for this project before we get right into this. The battery end of the powertrain should use heavier 14 gauge wire and connectors than the rest of the circuit. And that's because obviously it's 11 volts we're dealing with here at the start of our power, as well as the high amperage main switch. And as I mentioned, I don't have a spare one, so I'm using this massive toggle switch to merely represent. So I'll insert a photo here of the actual switch. And for those not very familiar with using LiPo batteries and their related circuits, please refer to a video I'll link above and below in the description about working safely with LiPo batteries, as they do pose a genuine risk of fire, shock, or even explosion in extreme cases. This circuit does not include a charging circuit, so that eliminates some of the risk, but there is still risk involved here, guys. And the rest of the wiring type can be your choosing, and most of the wiring will be done with JST connectors if you're using the PCB. And I prefer silicone wire where I can use it, and then stiff wire where it's needed, where you need it to hold its position and have a little bit of memory to it. In this final chapter of the video, I'll do my best to go over the order of component assembly, installation, using first these components, and then I'll do it again using Nova herself to show them installed. So there are videos in Nova's library covering most of this individually and a lot of the assembly and wiring and diagrams and such. However, again, a little outdated. They're still surely helpful for reference and example. So I'll pick out the relevant ones, and you're probably tired of hearing me say this, but I'll link them all below in the description, guys. So please check them out. Okay, so let's start at the battery. We have an 11.4 volt give or take battery where the whole process starts. Okay, from there we're going to go into high voltage connectors, and then that goes into our high amperage switch, which again, this is not it, but you should be familiar with it now. I showed a picture and I think I reviewed it in the parts list prior to this. So yes, the battery power first goes into our switch, which then goes into our high amperage buck converter to drop from our 11 volts down to 6.8 volts on the other side for our motors. Okay, then this power also directly from the switch here, which is the battery power, goes to our voltmeter so we can monitor the voltage of our battery. And then it also goes to the voltage divider on our PCB, which are these two resistors here represent. Or in the case if you're using the DIY boards, I have a separate little circuit board built, aka voltage divider, where the direct 11 volts would go into. Okay, and so then out of our main buck converter, we're going to go into our motor switch, because we've dropped down to 6.8 volts now. So that voltage will go into, or through, I should say, our switch to our PWM controller. And then obviously the motors get connected to the PWM controller. Okay, and then the 6.8 also goes out to our 5-volt buck converter to step down to 5.4 volts. And then the power from this board feeds our PCB, the appropriate voltage for the MPU units and other components. And there should be a terminal block here where that's connected. And then these terminal blocks here are basically power distribution for the 6.8. So the buck converter, the 6.8, actually connects to this terminal. And then I put 2 more terminals here to feed the switch to there, and then to feed this buck converter. And then in the case of the DIY boards, again, you'll have to create a little power terminal block to split out power for the various components, as well as each board has its 5-volt inputs. Okay, so yeah, the difference between these boards, I think, is obvious at this point. This new PCB not only is all JST connectors and makes things nice and tidy, it has a couple of switches here to enable and disable the reset switch and the I2C on the Nano for when you're uploading code. It carries the power block terminal. It carries the voltage divider. And then in between these two boards, there's 6 power terminals for 3 volt and 5 volt for various components that will need to power in the system. And the MPU IMU unit, I'm getting those screwed up today, also installs on the board. So it's a very simple board, very simple design. There's not much as far as circuitry going on here. It's more for the wiring of the JSTs and then to get all of these components on one board, which eliminates all 4 of these boards, the DIY boards. That being said, the Teensy circuit now, the first thing is within the circuit board, it's 2-way connected over I2C to the Nano, where it's the master and the Nano is the slave. Okay, and then as I mentioned, the MPU 6050 device is connected to the Teensy from the PCB. The MP3 player and the speaker are connected also to the Teensy. And then the NRF 24L01 for 2-way communication with Nova's DIY remote, also connected to the Teensy. There is a video out there because the latest, absolute latest version of the PCB does have the connectors pinned out for that device, for the NRF. However, this version that I'm using here, I didn't pin out. So there's one pin that's not out to a JST connector, so you actually have to hardwire it in this case. But again, there's a video to that, which I'll link to in the description, along with probably a dozen others at this point. Okay, and then lastly, on the Teensy, we also have the 3 PIR sensors are connected. And then on the back panel circuit of Nova, there's a few switches and potentiometers. One is the reset switch for the Teensy, and then the volume pot for the volume. Now here I'm just showing this is also kind of old school now, because over on Discord we've designed a different back panel where all these components fit in a nice little 3D printed plate, but this is the old school way of doing it. And hats off to Jordan, whom I give much kudos to for his help throughout this project. Okay, so that's the Teensy circuit and all the things that are pretty much connected on the PCB board. And as far as wiring goes, you'll end up with one JST wiring harness running to the head of Nova for all of the Nano components, which we'll go over now. One JST small wiring harness running to the lid of Nova for the PIR sensors, and then one JST harness going to the rear of Nova for all of the switches. So it comes out to be a nice clean assembly. All right, now for the Nano circuit. The SPI OLED is connected to the Nano. The 4 RGB LEDs connected to the Nano, and our 2 ultrasonic sensors, all through the PCB, again, obviously, and JST connectors. And then on the back panel circuit, we have the LED brightness pot and an on and off switch for the OLED screen. Okay, and then coming soon, I am still working on, we're going to be adding 4 thermistors to 4 of the motor points on Nova, at least to start with. That probably should do it, just to monitor the temperature of the motors, because I have noticed if I'm running Nova for 30-40 minutes, pushing the limits of her battery, but at the same time the motors really start to warm up if she's putting that much work onto them. So let's take a look at how the parts are installed in Nova and where they're installed, and a little bit of the wiring. So under the battery hatch, we have the battery. And I put a little piece of foam in here to protect my PWM controller because it is a quite tight fit. I've actually even put mine installed on its side for now. I'm debating on how best to install that. And this is the cage for the 5-volt buck converter, which I'm not going to remove for demonstrations here. And then this is the bottom of Nova. We'll get rid of that. And let's just disconnect our battery. And get that out of the way. Okay, so yes, that's where it all starts, at the battery. I believe this is 14 gauge wire, but this is what you should use all throughout the wiring until we get to the main buck converter. So from the battery, you saw me just disconnect it, which right here connects directly to our high amperage switch. Okay, and then the other end of the switch comes out and goes right here. I wired mine through the bottom, and then it goes through here to the top to the main high amperage buck converter, which we can't see right now, but I'll flip Nova over in a second. And then from there, it goes into the PCB and breaks off into that terminal block that I showed you previously, and comes back to the motor switch here on the back panel. And then from the motor switch, I also tap off and feed this display with the same motor voltage. So that should always read 6.8 volts, give or take. And then from this main switch, we come back through here again to feed the PWM controller. And at this point, we don't use the 14 gauge wire. Matter of fact, you wouldn't even get them into those terminals there. They're rather small terminals. So the high gauge wire is really just from the battery to the main buck converter. Okay, and then obviously all of the motors connect to the PWM controller, and that's where the wiring can get a little cumbersome and take up quite a bit of space for your battery, etc. I'm sure you guys will do a better job with your wiring than I did, but anyhow. And then, like I said, under here is the 5-volt buck converter, which also gets its power from the terminal block on the PCB. It takes in the 6.8 volts, and then it drops it down to 5.4, and then the power goes back up to the top to the PCB. And at this point, we can flip Nova over and take a look at the top side. There's our main high amperage buck converter. And then here is the terminal block where the buck converter drops down to 6.8, comes into this terminal right here for the terminal block. And then it feeds out these 3 terminals. Again, one going to the motor switch, one going to the display, voltage display, and then the third going to the 5-volt buck converter. Okay, and then we also have the main power coming into our voltage divider here so that we can monitor battery consumption or battery state, battery level. Okay, so now again, this used to be 2 PCBs squished in here. Now we have this cool 1 PCB. I still haven't even really mounted mine, guys. So as you can see, I've used all JST connectors. I have my back panel and front panel disconnected right now, but we could take a look at one of the wiring harnesses. So all the components in the head are wired up. And then I've grouped them all together into this bit of a harness, and it just passes through, sorry, wrong side. It just passes through the head and comes up through here, and then you plug in your JST connectors appropriately. Okay, so now the Teensy circuit. I'm going to try and do this in the same order that I just did it with the parts laid out. So the Teensy circuit first has its I2C connection to the Nano. That's on the circuit board, nothing to worry about. There is a jumper here to connect it to, just for sake of if I ever need to disconnect them. I didn't want it to be connected via tracks, but you'll see that in the wiring diagram. Then we have our IMU device, MPU 6050 down there, which is installed right on the PCB. Then we have our MP3 player and speaker. You can't see the player, but I'll do a little zoom shot here of it from another camera angle. And then we have our NRF 24L01 right here. I have not really installed mine. I still just have it resting here because a few users have had issue with interference, and I'm pretty sure it would come from the buck converter. So, but secondly, you don't want your wires too long for its connection to the Teensy, so it's a give or take. I mean, ideally, yes, it would probably be better off, in the head. I don't know why I keep thinking that's the head. Because the tail also is where the battery connection is and the high voltage lines. So the best place would be up in this cavity. But again, I didn't want to extend the wiring, and mine works fine in this corner. So for now, I just have it sitting there instead of mounted. Okay, so next would be the PIR sensors. So here is the lid with the PIR sensors installed in it. Hopefully this is staying in focus, guys. And here we just have the 3 PIR sensors, and they share power. So there's one lead for power, and then the other lead for their connections to the Teensy. So that's pretty simple. Again, just plugs right into the PCB board. And if you are using the DIY boards, there's JSTs for that as well. And on the back panel, we have the reset button for the Teensy, as well as the volume pot for the MP3 player, both of which have their own wire harness. Again, I haven't disconnected the rear one, but they come up here, and the reset button and the volume switch both connect to the Teensy circuit. Now the Nano circuit, starting on the head, we have our SPI display. Then we have our 4 RGB LEDs, 2 on either side, and then our 2 ultrasonic sensors. And that's a fun little wiring project. Let's see if I can keep this in focus, hopefully. Yeah, the RGBs, if you'll notice, are daisy chained together. So it's just one main lead coming out for the 2 of them, the 2 pairs, the 4 of them, if you want to say that. And then you have the 2 ultrasonic sensors, and then the SPI display in the center. So it is a little fun to wire. I used a combination of silicone wire and solid cord wire here just to keep things intact nicely. And then I've also put connectors here so that I can disconnect my whole wiring harness from the head if I want to. That way, uninstalling the head, I can either disconnect it here and pull the head off, or disconnect the harness and pull the whole head and harness out like I've done here. So that's a little tricky to wire, but once you get it going, you'll be good to go. And unfortunately, in this case, the RGB LEDs and the ultrasonic sensors and their holders get glued into place, which I'm not a fan of super glue in any respect. And obviously, the drawbacks of gluing things in place are if one of those guys break, it's not the easiest thing to replace. But they're electronics, no moving parts. So as long as you don't burn it up, they shouldn't break. Okay, and then to finalize the Nano circuit, on the back panel, we have a brightness pot for the RGB LEDs. And then we have on-off button for the OLED. I chose to make mine embedded, so you have to use a pin to press it. The only purpose of that switch is in case your battery's running low, you're out on the road showing off your robot to somebody, and you want to save a little power, you can disable your OLED. Okay, so yeah, that's all the parts, guys. Hopefully that makes sense. I understand that it would have been nicer if I had done nice instructional videos step by step as I assembled everything and talked about each and every wire, but I've done a really good breakdown video where I did go through every single piece and talked about every wire and referred back to the wiring diagrams to show it on the diagram as well. Now there are a few things that aren't included in that because it's a little outdated, which would be the NRF module, and heck, that might be just about it. Yeah, so I'll link to that in the card above and then in the description below. That's a really good video to watch if you need some extra help with wiring and understanding the wiring diagrams. Okay, everyone, so that pretty much wraps up the hardware and wiring video. Again, I realize it's not in great detail, so if there's anything that I missed and didn't discuss that you'd like me to do, please leave a comment below and I can probably do that for you. Last comment is, when you're finishing up your wiring, and I probably don't have to say this, but make sure you use shrink wrap where needed, and then when you're completing your wiring and understand how it's all going to go into place when all the covers are on, you can attach wire ties to help. And then to finish things off, you can even, on the outside edges here, which you've probably seen in my previous videos, you can use this wire wrap to make it even look more pretty. And yeah, that's going to be a project to project decision. So, alright guys, thanks for watching. Like, share, and subscribe. This will wrap up video number 3 in the build series. Number 4 coming in a week or two on the software and how to set that up and configure it, and calibrating your motors, etc. So again, thanks for watching. Take care of each other, and I'll see you soon.